We are going to talk about simplifying square roots with variables. Okay, so a lot of this is going to look very familiar, except now we have just added variables with exponents into the mix. Okay, so before we start looking at square roots when we have variables underneath the radical, let's just take a minute and talk about a few things with variable powers. Okay, so if 4 squared is 4 times 4, then we can apply that process to variables. So that would mean x squared is x times x, right? And x to the third would be x times x times x. X to the fourth means we have 4 x's that are multiplied. X to the fifth would mean 5. So if x squared equals x times x, then we could say that the square root of x squared would equal x, right? Because if I'm square rooting x squared, and I look back at the factors would be x times x. That's a pair. And if you remember from simplifying non-perfect roots, you do want to look for perfect squares. And if you factor all the way down to a prime factorization, you'll see pairs of factors. Okay, so because x times x is a pair that creates a perfect number, then we can square root that. So if we look at x to the third, we have a pair here. So when I try to take the square root of x to the third power, well, I know I have a pair of an x times an x, so I could break this down into x squared times x, right? That's where this green circle, the x times x inside, comes from. And the square root of x squared is going to be x, right? So this would equal x times the square root of x. If we look at x to the fourth, if I took the square root of x to the fourth, if I look here, I have 2 pairs. So we wouldn't have to break this down. You could go straight to saying that, well, the square root of x to the fourth would be x squared. Or you could look at it like this as well, x squared times x squared, because that shows our pairs, right? The square root of x squared is x. The square root of x squared is x. X times x is x squared. Okay? Now, when you see me drawing the radical around these multiplication problems, remember, you can visualize this as square root of x squared times square root of x squared as well. That was something that was talked about when we were doing the introduction to the roots and the radicals. Okay, so for x to the fifth, if I look here, I have a pair here, and an x left over. So when I take the square root of x to the fifth, this pair, when I square root the x times x, I'm going to get an x. When I square root this x times x, or x squared, I get another x. And this little leftover guy is by himself here. So I end up with x squared times the square root of x. So a couple things you'll notice, obviously, that whenever we have an even exponent, there are no square roots left over, right? When I have x to the fourth, I ended up with x squared as the square root. When we had x to the fifth, I had a number in the square root left over. So those are some patterns, hopefully, that you see. So when we take the square root of an even exponent on our variable, then we should end up with our number outside of the radical. All right. If we looked at x to the sixth power without, all of this extra kind of following the patterns here. So if we just follow the pattern, we've got x here, x times x squared, x squared times square root of x, right? I think I maybe said this one wrong. X times the square root of x. Then we have x squared. Then I have x squared times the square root of x. So I can assume that the next one would be x to the third, right? If we kind of look at the pattern and follow it. If I have x times x times x times x times x times x, and we pair things up, I have x times x times x. This is when I square root it, right? So I would end up with x to the third power. So basically, if I have an even exponent with a variable, cut the exponent in half, right? So keep that in mind as we go through our examples in a little bit. We do have kind of a general, not necessarily rule, but I have some things I want you to write down. So given the square root of x to the m power, if m is a multiple of 2, use the rule. Square root of x to the m equals x to the m over 2. And that's what I was just saying, is that if we have an even exponent, we just cut it in half, right? So then let's put to words what happens if m is not a multiple of 2. So if m is not a multiple of 2, use the rule. I'm going to have to move this down a little bit because it's kind of tall. X to the m equals x to the m minus 1 over 2 times the square root of x. So let's go look up above for a second to make sense of what's happening here. So let's look at this. This was x to the 5th, or the square root of x to the 5th. So if my exponent is not a multiple of 2, where it says, right down here, m minus 1 over 2, that just means take the exponent, go 1 less, divide it in half. Okay, so if we look here at my 5, so I'm going to take 5 minus 1 over 2, which is 4 over 2, which equals 2. That is where this 2 comes from. And then I've got square root of x here. Okay, so that's kind of how that works. And we'll see it in action in just a few minutes as well. Okay, so basically it's just saying take the exponent, take 1 away to make it even, divide it by 2 to get your exponent for the outside, and then you have the square root of the variable left over. And that comes from the one that you subtracted. All right, so let's just jump into an example. Example 1, square root of 25, x to the 6th, y to the 13th. All right, so let's break this down. We're going to kind of split this up just so that we can focus in on each part. So square root of 25, square root of x to the 6th, square root of y to the 13th. So now square root of 25 is going to become 5 because it's a perfect square. Again, if you have not memorized those yet, you want to memorize those. They will come in handy over and over and over for the rest of the years you take math. X to the 6th. Now, m is a multiple of 2, so we're going to use the rule x to the 6th over 2, which becomes x to the 3rd, right? It's just the exponent cut in half. Now for the last one here, my exponent is not a multiple of 2, so we're going to use this little rule right here. So I'm going to say y. Of course, in the rule we wrote an x, but that can be replaced with whatever variable you have. So y to the m minus 1 over 2 times the square root of y. So let's kind of put it all together here. And we get 5x to the third, y, 13 minus 1 is 12, 12 divided by 2 is 6, square root of y. Now, if that's a little bit too much, that's okay. All you have to do is just expand everything out and match up your pairs. So we're not going to do this on every single one, but as an alternate, if that formula is a little too much, you could spread the whole thing out. So I could take 25 and say 5 times 5. I would have x multiplied by itself 6 times. And I have y multiplied by itself 13 times. I guess I could have picked a smaller number. 2, 3, 4, 5, 6, 7. Just make sure I have the right amount of y's here. So we could split this all out. And of course, this looks crazy, but it's always good to know that you have a backup plan if something happens and you forget what to do, so that you're not thinking, well, I'm just going to give up. I don't know what to do. You can always go back to basics and just expand everything out. And then you look and say, okay, I'm looking for pairs. So I'm just going to match up as many pairs as I can find. Pairs of factors. And so if I look here, if I have a pair of 5s, then I know when I square root it, I'm just going to get a 5 left. I have a pair of x's here, a pair of x's here, a pair of x's here. So that's going to be 1, 2, 3. So that's x to the third, right? Then for the y's, I have 1, 2, 3, 4, 5, 6 pairs of y's. So that's y to the 6th. And then I have one little lone y left over. That stays under the radical. Same exact answer that we got before. It takes a little bit longer, but like I said, if you are unsure how to handle the different situations, just go back to basics and spread it out. Nothing wrong with that. Let's look at another example. Square root of 40, a to the 19th. Okay, so we're going to break this down into square root of 40 times the square root of a to the 19th. Make sure that looks like 19. Okay, now 40 is not a perfect square, so we've got to figure out what perfect squares are within 40. So maybe you have memorized your perfect squares and you see that it would be 4 times 10. That's perfectly fine. So what you would do if that's the case is we know that square root of 40 would become 2 times the square root of 10 times, now a to the 19th. That's going to become a to the 19 over 2 times this, 19 minus 1 over 2 times the square root of a. So then we get 2a to, let's see, 18 divided by 2 is 9 times the square root of 10a. Okay, so just as I can multiply the 2 times the a to the 9th for this portion, I can take square root of 10 times square root of a and get square root of 10a. So I can multiply those back underneath, right? Because if I have square root of 10, if I had square root of 10a, I could split it up into square root of 10 times square root of a. So I can go back the other direction as well. That's why I can kind of put those together there. Now, if you struggled to find the 4 times the square root of 4 times the 10 over here, And all you have to do is we can just break this down into a prime factor tree. Square root of 4 times square root of 10. And I just keep factoring down until I get prime numbers. And then once I get prime numbers, then I can go and find the pairs just like we did up above. I have a pair of 2's here. So if I have a pair of 2's, that's going to be square root of 4, which I know becomes 2. There are no pairs left, so I just multiply the 2 times the 5, and I get square root of 10. So that's another option with how to break down numbers that are not perfect squares. You can use what you learned in yesterday's notes to help with that portion. The last example I want you to see is kind of a big one. Square root of 128, p to the 5th, q to the 2nd, r to the 18th. Okay, so for 128, we need to find the perfect squares within 128. This is purely based on math facts, what you know. If all else fails, we always know that an even number is divisible by 2. So 2 times 64 is 128. Now, if you know your perfect squares, you know that 64 is a perfect square. So right out of the gate, now I've been writing these horizontally, now I'm going vertical, just in case you're a little more comfortable with that. That way you can see some different methods. So 128 would break down into 8 times the square root of 2. If you completed the factor tree like I did over there. Now let's say that you didn't remember that 64 is perfect. You can just keep working it down. 64 is 8 times 8. And that breaks down to square root of 4 times square root of 2. Square root of 4 times square root of 2. And actually, if you notice here, I've got a pair of 4's there and a pair of 2's there. So that would give me 4 times 2 times my lonely little square root of 2 up there, which still gets me 8 times the square root of 2. Okay, so you have a lot of different options. So then for the p to the 5th, it's going to be p to the 5 minus 1 over 2 because it's odd, right? Times the square root of p. Q squared, that's an even, so that's going to give me just q. Right? We take the exponent over 2, we divide it in half. R to the 18th, 18 is even. 18 divided by 2. So my final answer here is going to be the 8 times p to the 2nd times q to the 1st times r to the 9th, right? So 8 p to the 4th times q. I don't need to put the, not p to the 4th, p to the 2nd times q times r to the 9th times, and then I have my 2 and my p here, square root of 2p. When they get so big like this, also please make sure that you keep track and double check that you didn't miss anything. Okay, I got my 8, I got my p, q, r handled. I got the square root of 2, the square root of p, nothing left out, and that's it. One last thing, this also does work with decimals and fractions. Just in case, let's do actually a quick example 4. So let's say 4a to the 3rd over 25 b to the 5th. No, let's say b to the 4th. Okay, so in this case, we can break everything up just so we can kind of keep track of it all. So square root of 4 times square root of a to the third, square root of 25 times square root of b to the fourth. Square root of 4 is going to become a 2. Square root of a to the third is going to become a to the 3 minus 1 over 2. So we're going to end up with a to the first power, right, times square root of a. And on the bottom, we've got 5 times b squared. And that's it.